Hello and welcome back. So, this video we're going to look at some of the metrics that are optimized in order to estimate the parameters of the transformation. Correct. So, the last video we saw a few simple transformations that are typically applied. So, for instance, translations and then rotations. We also had looked at the affine transform, which had n cross n matrix along with the translation. So the elements of that matrix are typically the parameters of the transformation matrix, that is, are the parameters that we typically estimate. So for the rotation matrix, we had the sine theta, cosine theta matrix. So where theta is the parameter, then this tx, ty, these are translations that we would estimate. And then and for affine transform, we had an A matrix, for instance, which had n cross n parameters. So in this case, it will be 2 cross 2 or 4 parameters. So Aij. So it will be 4 parameters, right? So these parameters have to be estimated based on optimizing a metric. And there are several metrics that are used, but we are going to look at image intensity based metrics typically that are often used, especially in the context of rigid body registration. So the first one we are going to look at is the mean squares metric. You can also call it the least squares metric, wherein the formula is given here. Let me just simplify the rotation. S refers to the metric. Of course, we are treating it as a function of P, which are nothing but the parameters of the transformation that we are trying to estimate. F is the fixed image, M is the moving image, T is the transformation itself. Okay, so we'll see how it comes into picture. So the generally, if we have total number of n pixels, once again, this is some abuse of notation because we are using capital N in the previous lecture where we looked at n refers to the dimensions of the image, but here in this case we are only n refers to the number of pixels in the image. So all the pixels, we are going to look at the least squares difference between the fixed image and the transformed moving image. So every pixel so we are mapping every pixel in xi with this transform t and estimating the moving image at those points, and see after estimation whether the images match. Okay, now here actually I've skipped a step, in the sense that the interpolation step. Okay, I have not done that. Maybe we'll go back. We will look at this interpolation step maybe in a later slide, right? A later lecture, sorry, not later slide. So here what happens is, once you do the transformation on xi with this t, it will give you a physical coordinate space. But physical coordinate will not exactly map to a pixel index. So there will be some error there. And so you will have to do an interpolation to estimate the pixel intensity values at t of xi comma. So after the transformation. So this part is where interpolation comes in. Typically you use linear or bilinear interpolation. So we won't get into the details, but we can talk about it in a later lecture. Okay. So this is just to clarify the notation, is there is a spelling mistake here. It's the ith pixel in the image. X of I is the ith pixel, not the 9th pixel, and n capital N is the total number of pixels. Okay. So from this formula, how are you going to estimate? So we're going to have to minimize this loss function, this mean squares loss, in order to estimate the parameters P of the transform. So if you do that, so for instance, here again there is some error. Here it's actually delta S over delta P is given by this formula. Okay, so I'll clarify this formula here. So you have the delta S. This is not correct. Sorry about the error. So this is actually your delta S over delta P. Okay, it's given by this expression. So it's actually the difference between the pixel intensities of the fixed and the moving image after transformation. There is this delta M over delta X prime. This is nothing but the gradient, numerical gradient. We saw how it's evaluated of the moving image. And this is the Jacobian of the transformation. Okay. So how do we get here? So we'll just look at one. We will just see how this works out in 1 second. Okay. Okay. So we will write this down. This the least squares loss function for one pixel. So this Si is basically for one pixel will be f of xi minus m of xi prime squared. Now this xi prime I'm writing is nothing but this transform, right, coordinate. So now if I do delta Si by delta p, then you have 2 times f of xi minus m of xi prime times delta m by delta p xi prime. So I doesn't come out well most of the time. So this is the formula. So now if we look at the delta m by delta p, this xi prime, we can rewrite this using chain rule as delta m by delta xi prime plus xi prime is a function of p, right, because we have seen this here, times delta xi prime by delta p. Now this is your gradient. This is the Jacobian of the transformation. Okay. Now we look at, when we say gradient, what do we mean? There will be typically be so many components, right? So let's say two-dimensional image, you will have delta m by delta x, delta m by delta y. And what about the Jacobian? The Jacobian will have two rows and as many columns as there are parameters. So let's say we are considering two parameters p1 and p2. So, or let's say three parameters, right? So you will get delta x prime by delta p1, delta x prime by delta p2, delta x prime by delta p3, and then you have similar thing for y. So I'll just let me just wipe this out and rewrite on the other side so that it's. So this is the gradient. So let's just for the gradient for the Jacobian you will have in this case. Let me just write this as 2D, right? So you have delta x prime by delta p1, delta x prime delta p2, delta x prime delta p3. Similarly, delta y prime delta p1, delta y prime delta p2, delta y prime delta p3. Right? So you have, so then what you do is you take dot product with each this will be dot product with each column. So you'll end up with a 3 vector, 3 components, each corresponding to the gradient of S with respect to, so these will correspond to delta S over P1, delta P1, delta S over delta P2, delta S over delta P3. Okay. So then what you do with this, so you would then do gradient descent step, right? So that step, let me just quickly add that. So if just to recap what we did there, you will get this matrices. Let me rewrite this so that you can. So you will have the moving image gradients, then you have the Jacobian of the transformation, right? Delta x prime by delta p1, delta x prime by delta p3, then you have delta y prime by delta p1. And you multiply row column, right? So you'll have 3. So you'll end up with 3, which would correspond to delta S by delta P1, delta S by delta P2, delta S by delta P3, right? So then you would do the gradient descent step, which is basically Pi goes to Pi minus some lambda times delta S by delta P. Yeah, that's how you would do the gradient descent to estimate the parameters. Okay. So we'll see that this is the recurring case for all the other things that, for all the other loss functions or metrics that we will use. Okay, so the other metric which is basically dependent on the intensity is the normalized cross correlation. So once again, this minus sign is used to make it a minimization problem. Typically, you want to maximize the correlation between the moving and the fixed image after you do the transformation. But if you want to make the minimization, so what gradient descent does, you put the minus sign in front. The maximum value of this particular expression. So basically, you are multiplying them pixel by pixel after transformation, and then you are normalizing it with their squares in respective squares. One of the things you do not shown here is you would subtract the mean. So you would actually fxi minus f bar will be done, m of xi minus m bar will be done. So this m bar and f bar are nothing but the mean of the images. This particular technique makes this metric immune to arbitrary DC shifts in the images. Okay, you can multiply every pixel value by some arbitrary constant or add any arbitrary constant to the pixel value, and is robust to that. Okay, so once again, you can go through and do the calculation delta S or delta P. Like I said, this is an important step because once you figure out delta S by delta P, all you have to do is P goes to P minus lambda delta S over delta P. This is the gradient descent step. So once you take this step, then you once again evaluate this metric, calculate how much you have to move. You also have to parameterize this lambda, this hyperparameter lambda, you have to adjust based on the problem. Okay, so this normalized cross correlation is also used. Both this least squares metric and normalized cross correlation very good to use if you are looking at same type. So for instance, if you are going to do CT to CT or CT to MRI, not CT to MRI, I'm sorry, please strike that. MRI to MRI, or basically you are trying to align images from the same imaging modality, 2 CT image, and in fact intra-subject it's even better. Okay, so that's a very good, these two are very good metrics to use when you're trying to do this kind of alignment. Now the problem starts when you're trying to do CT to MR, CT to PET, MR to PET, or CT to ultrasound, MR to ultrasound. There the pixel intensities or voxel intensities are completely different, and these metrics might not work as you might expect. Okay, so in that case, what you do, so that's when you have this particular metric called mutual information. Okay, the mutual information is defined in terms of entropy of an image. So what is the definition of entropy is given here. Let's say you have two images, in this case A and B. The entropy of each of these images are given by these formulas. Of course, this is in the continuous domain. If for the for a discrete domain like in an image, this converts to a summation over the pixel values, right? Or the various bins in an image. So how do you estimate this probability density functions, this PA and PB, or the probability density functions of an image? So these are typically estimated using the histogram. Okay, very simple way is to construct an histogram. There are, of course, there are some kernel based methods you would do to actually estimate this, make it into a continuous function. But histogram is a pretty good way of doing it. So what this mutual information, that we want to maximize mutual information, and how does this work? So you might ask, what is the idea behind maximizing mutual information? Is the question that we will try to understand here. So what we are assuming is that, let's say we have this case where these two images we assume are independent. Okay, we assume that both these images are independent, right? So then let's just go before we go here. So let's assume that these two images are independent. Then the joint probability of these two images, okay, the joint probability of these two images, given that they are independent, have nothing to do with each other, is basically, or that they are not correlated at all, is that it's the product of the individual probability distributions. Okay, so if the images are not correlated, or in this, I should say more specifically, I should say the images are independent of each other, you cannot predict anything about one image using the other image. Correct? So you have fixed and moving image, and as assume that you can predict nothing about the moving image using the fixed image. then you have the joint probability of those two images, pixel values of those two images is given by the product of the individual probabilities. Here, these are the probability density functions corresponding to the pixel intensity values. Okay, so what is the probability of a certain pixel having a value 100? That's what this shows. Okay, so these A and B's are nothing but pixel intensity values. Okay, so we are treating them like random variables. So the joint. So if you look at the what I can call the joint entropy, right? And the joint entropy h of b in this A comma b is given by the sum of their. Okay. Now let's assume that in the case that they are not independent, right? If they are not independent, then we can easily write this down. We can write this in this form, because there's an extra term that comes in which is excluded. So h of a comma b is less than h of a plus h of b. Okay. Now what we want to do is look at this difference. Look at this difference. Okay. But this is what we call mutual information. And we want to maximize this difference. Okay. So because what we want to be able to do following registration is that we should be able to say something about the moving image based on the fixed image. That's what we ideally want, right? That would suggest a very good registration. Okay. So then the idea is to make this difference bigger. So we want to be as far away from independence as possible. That's the goal. So then we want to individually maximize these entropies while minimizing this entropy. Okay. So this is the joint. So we have to minimize this joint entropy while maximizing the individual entropies. Okay. So from the point of view of understanding what the image entropy means. So if you consider, let's say a distribution of pixels which are, I'm going to just draw a very simple picture here, right? We have, let's say, 10 pixel levels. Okay, 10 pixel levels. I'm going to draw all 10 of them, but anyway, some n pixel levels. And all of them have the same probability. Right? So this is, let's say, the probability axis. This is the intensity. Okay, this is a random variable and its corresponding probability. So I'm just putting one arrow there just to see they are all the same. So this has very high entropy, because it's very difficult for you to predict. If you point to a particular pixel, you can't predict its value with a great confidence, because it's all pixel values are equally probable. On the other hand, let's consider a pixel distribution which looks like this, very sharply peaked, right? Once again, this is the pixel intensity bins. The probability, you see that we can with some degree of certainty predict the pixel value. Okay, this has low entropy. Okay, so we actually want to increase the entropy of these individual images that are being registered, especially in the region of overlap, because this high entropy means that you have a very heterogeneous region in the image region. That's what this high entropy translates to. And low entropy translates to a very uniform, smooth region. Okay. So we want to be overlapping in both the cases. The region of overlap for both A and B, or fixed and moving image, should correspond to regions of high entropy, which means they have some structure there. That's the one we want to be matching. Okay. On the other hand, when you consider the joint probability distribution meaning what is the probability that a pair of pixel intensities co-occur. The co-occurrence of pixel intensities, that's what we typically would mean by this joint entropy, and the joint distribution of these pixel values, and you want them to be sharply peaked for maximum alignment, correct? So if they are aligned properly, then you will see that the 2D histogram, so we are looking at a 2D histogram, will be a very sharp histogram. Okay, so what do I mean by sharp histogram? Let me just draw this quickly. So if you have the joint histogram, which means that you're looking at probability of co-occurrence of pixel intensities, right? So here, when you say PA of A, you're just looking at a particular pixel value A and its probability of occurrence. You just count the number of times the intensity occurs. Or there are other ways of also doing this. If you have a range of a continuous range of intensity values, but we won't get into those details. But as far as the joint histogram is concerned, you have, let's say, two axes. It's a 2D histogram. So you're looking at, let's say in this case, intensity along of A, right? Intensity values from A, intensity values from B here. And then you're looking at a histogram of these pairs of values occurring. We count the number of times a pair of values occur together divided by the total number of pixels. Now, in that case, you want a sharply peaked histogram. When I say a sharply peaked histogram, so if you look at this in 2D, they have two axes corresponding intensities from each of the images. So it would lie the high probability region should be here. So it's a sharply peaked because this is the high probability region. Everywhere else it will be very sparse. So in a sense it will be close to zero here. So you have to think of it in the 3D where this shaded portion is basically rising out of the plane of the screen. Okay. So this implies very bright, very large values of probability, and in other regions which very low values of probability. Correct. So this is what I mean by a sharply peaked histogram in 2 dimensions. So there will be a thin line, but which very the probability here in this region is very high. Probability outside this region is very low. Okay, and if the images are not properly aligned, then you will have that this becomes slightly worse, in the sense you will have a much larger region with higher probabilities, or in this case the probability is spread all over the place, like a uniform probability. It will look that way. So this particular situation I'm talking about, this blue band is similar to what I've shown here for one image, and this other situation where I've shown this red region where you have a lot of co-occurrence of these pixel intensities are equally probable, right? That corresponds to a poor alignment. This has been observed empirically also. So for optimizing this IAB, you would expect HA and HP to be high and H of A comma B to be much lower. Okay. So this concludes our look at different metrics used for image registration, especially rigid registration, wherein we are looking at just rigid body transformations, rotations, translations, maybe some affine transforms. We are looking at cases where we are doing inter-subject registration for the same patient with the same imaging modalities, wherein we can use normalized cross correlation or just sum of squares, least squares. In this case, if you have different imaging modalities, then you can use the mutual information as a metric for image registration. Okay, thank you.